It is an honor to be here to give this first keynote of this morning to you. As John hinted at, I come from the fields of risk and safety science. I don't know much about web performance and web operations, so please forgive me if my examples might seem a bit premature to you, but I hope that I can use them to make my points across to you this morning. So my topic here is what, where, and when is risk in systems design, in web operations. And I've also published a connected blog post at O'Reilly for you to check out if you like. And I think that what time will allow me to do here this morning is to outline two pretty extreme views on how to interpret risk in web performance and web operations. And the first one, the first view of risk is risk as a product of unreliable system components. And we will see where this will take us and then contrast it with risk as a product of nonlinear relations and interactions, in saying risk as a product of complexity, basically. And I've drawn some kind of a pretty ugly looking mind map for us to use this morning. And taking us in both directions, we will see some principles of these two views, and we will in both cases end up with some strategies for how to manage risk given the respective perspective. So let's first look at risk as a product of unreliable system components and see how we could play with that for the field of web operations. Inherent in this idea of risk is an organizational model of organizing web operations based on a machine metaphor principle. Basically saying that what you are to do in web operations is to mimic as closely as possible the workings of a machine. And the machine has some specific principles for it to adhere to in order to organize efficiently. And the main principle is that if you want to understand why your organization, your machine, is working or why it is not working, what you do analytically is that you go down and in. You go down and in to have a look at the individual components, how they interact linearly and how well they follow their design rules. Those are some of the main principles or main targets of what to look at when understanding why the organization is working or why it is not. And when it is working, we say that it works reliably. That's the ultimate aim of the machine of web operations, if you like. And web operations is working reliably when all the individual components stick to the rules, which is pretty much a matter of designing the proper rules for it to stick to. Reliability then becomes something that the machine of web operations has or is. It is reliable. Per design, it is reliable. And the reductionist principle follows that the functioning of the whole can be reduced to the functioning of the constituent components. Essentially, that if the machine of web operations is not working, there needs to be an individual component which is not working. So, which one is the most unreliable component of web operations? Which one is it? I've Googled my way around, looked at some post-mortem accounts, and we can look at a few. Here we say Amazon cloud outage triggered by human error, right? That gives a hint. Another one, Twitter outage caused by human error, all right? And final one, oh, surprise, surprise. Amazon blames human error for Christmas Eve outage. So from these, by me, highly cherry-picked examples, it seems that the most unreliable component of web operations is often constructed to be you guys. The unreliable individual human actor of the system, the programmer or whatever it might be in your case. So this idea of risk as a product of unreliable system components does not only allow us to identify the most unreliable one, but it also allows neatly for us to calculate risk as a function of the severity of the failures that you cause by your unreliability and the unreliability. So the probability and severity of the event that you cause, that's the function we use to calculate risk, and we can then illustrate risk as is done here with a risk matrix, for instance, where you have the two dimensions of probability and severity, and then you can plot all the individual failure scenarios that you have identified in this matrix. Or you do, as is done in this simple example that I found on a blog, you calculate the risk of Foursquare going down during a year to one specific number, multiplying probability and severity. In this case, the probability being 3.5% during a year, and the cost $1 million, and then it's an estimated risk of $35,000. That's simple as that. So this idea of risk as a product of unreliable system components neatly allows us to construct risk as a function of severity and probability of failure. And it also has some underlying ideas for how to manage risk. And I will show two to you here this morning, the use of redundant barriers and the idea that we can then reduce your unreliability or the variability of the system. And let's first look at the use of redundant barriers. A strategy very physically graspable to us working in the traditional safety sciences, where we have worked with industries such as process control and transportation, healthcare, where we have clearly physical energies, harmful energies that we need to keep contained from vulnerable targets like us humans. And we do so by building multiple layers of defense. We call it defenses in depth, multiple barriers. Jim Reason explained in the 1990s that also these barriers have a certain degree of unreliability to them, and he illustrated that by making holes in them, and that's how the Swiss cheese model of accident causation came to be, that at one point these holes might line up, putting the harmful energy in direct contact with the vulnerable target, and that's the concept of having an accident. And this way of reasoning we also use when we make quantitative risk analysis. You see here an example of an event tree for a fire occurring, and you can see all the barriers illustrated by nodes in this event tree, and you can see the amount of holes in them illustrated by the probability of them maintaining their function in the event of a fire occurring. So very neat, this idea of risk as a product of unreliable system components in order to manage risk through the use of redundant barriers. The other principle is that if we have constructed risk as your unreliability, then what we do to manage risk is to reduce that unreliability, or to reduce the variability of the system, if you like. We can do so by simply replacing you unreliable humans with some more reliable technology. That we see here in this blog post entitled Outage Prevention, Taking Humans Out of the IT Equation. Don't know how that would look in practice, but you might have some ideas. We could also control you or replace you by more reliable rules, or simply ask you to try harder, to be more reliable, to appeal to your motivation, for instance. That's also a quite popular risk management strategy to use when constructing risk as a product of unreliable system components. So those two strategies, the use of redundant barriers and reducing variability, are the most typical ones used when constructing risk as a product of unreliable system components. So let's look at the second idea then here. The idea that we can construct risk not as your unreliability, but instead as a product of non-linear interactions and relations, essentially risk as a product of system complexity. To do so, we need a complete different set of metaphors. The machine metaphor doesn't really work here. And the metaphor that we typically use is the metaphor of a living system in order to construct risk as a product of nonlinear relations and interactions. And the living system works from a complete different set of principles than does the machine. Here we do not work with linearly connected components. Here we work with a diverse set of actors who shifts between being loosely and tightly coupled, who shifts between being highly interdependent and highly independent, constantly and dynamically so. For you, you could probably come up with many examples of when this is a case. For instance, services like Netflix, Foursquare, Quora, and Reddit are, to a certain and varying degree, dependent on the workings of Amazon, for instance. Sometimes more, sometimes less. Probably very much so on a Christmas Eve, for instance. So the functioning of the whole can no longer be reduced to the functioning of the constituent components. We need to look at the interactions and relations between actors rather than the reliability of each actor. This system does no longer allow for a complete description of it to be made, partly because it is so constantly dynamically adapting to its environment. It is constantly changing. But also because no actor in a complex system can grasp the complexity of the entire system. That's theoretically impossible for it to happen. And also, the system doesn't allow for a complete description because depending on which actor you ask to describe the system, you will get qualitatively different descriptions back. So it's a matter of whose perspective do you take? And we need to understand those relations and interactions now. That's where we focus. And indeed, it is also so that the use of more barriers might be a problem here, because more barriers actually might increase the number of interactions in this system. And if we see risk as a product of interactions, then more barriers might actually increase risk. So the use of barriers is no longer non-problematic to use as a risk management strategy. These are some of the principles of a complex system, of web operations maybe as a complex system. And I will spend the rest of this talk outlining a few more ideas connected to this idea of web operations as a complex system when discussing risk. And I will specifically focus on two topics. The first one being the path dependency of risk as a path-dependent process, if you like. And the second, risk as a control problem. And we will see where that might take us. Let's first look at risk as a path-dependent process. Essentially the idea that history matters. In order to understand risk, we need to understand the history of that risk that we are trying to understand. And one example that I found from your world would be this one, a BBC coverage written by the technology reporter Leon Keelian, entitled "Why Banks Are Likely to Face More Software Glitches in 2013." And in this coverage, Leo interviews Lev Lesokin, the strategy chief of Cost, who really appeals to history in his accounts of the current software risks that the banking industry run. Look here, he says software is inherently difficult, and for developers who are dealing with systems which have been added to, cropped, and changed over the years, it is a struggle to see where faults in a system are most likely to lie. Definitely appealing to history in order to understand current risks. And also, he embraces the idea of no single actor being able to grasp the complexity of the whole, saying that no single person or even group of people can ever fully understand the structure under the key business transactions in an enterprise. I think it's nicely formulated. Another example of the path dependency of risk, not taken from your world, but rather from the worlds that are typically thought of when we work with safety science, and this is from the transportation industry. And this is the example of a letter written by the mayor of a little Italian island called Giglio in August 2011. And this letter was written to a cruise shipping captain at a shipping company called Costa. And in this letter, the mayor of the little Italian island thanks the cruise shipping captain for an unequaled spectacle that has become an indispensable tradition. Indispensable tradition, really appealing to history here. So what is this indispensable tradition? You might get it already. Well, it's the unequaled spectacle of making close flybys, saluting certain islands and cities. And we know the scene some 5 months later outside this very island of Giglio, when Costa Concordia grounded right there, with another captain on board, I should say, than the one who received the letter with a thank you for the unequaled spectacle that has become an indispensable tradition. Another captain, but an event where we mainly construct him now as a crazy sex addict idiot, completely lacking any sort of seamanship. The unequaled spectacle that has become an indispensable tradition tells a different story. Tells a different story about the path dependency of risk. And we might have different notions to work with here. In your world, you use the term technical debt, for instance. And I think that might be highly appropriate to discuss the historical trajectory of certain risks. In safety science, we use terms like a normalization of deviance based on Diane Vaughan's writings. A normalization, risk as a normalization, as a process of changing what is normal and what is norm in an organization. An indispensable tradition. Normalization of deviance. We also use terms like practical drift or drift into failure that you might have heard. So that's about the path dependency of risk, the importance of considering history when discussing risk in web operations, maybe. And we will also look at risk as a control problem, which I think could be interesting to you in web operations, where what you do is that you try to constantly experiment to optimize locally in a highly goal-constrained environment, which is what this model by Jens Rasmussen tries to illustrate. A goal-constrained environment where you are not to cross, you see on the top, the boundary of financially acceptable behavior, because that's when you get bankrupt, where you are not to cross the boundary of unacceptable workload because you're burned out, and where you are not to cross the boundary of functionally acceptable behavior or acceptable risk, because that's when you have an outage. That's when you have an accident. And there are a couple of important things to note here. The first important thing is that the only way that you can get definitive feedback on where any of these boundaries is by crossing it. That's the only way you can know where the boundary of acceptable risk is by having an accident, essentially. But also, this model says that each of these boundaries creates a pressure away from the boundary. So, the boundary of financially acceptable behavior creates a pressure towards efficiency, pushing away from the boundary. The boundary of unacceptable workload creates a pressure towards least effort. And together, these two forms a gradient towards the boundary of unacceptable risk. So how do you push back? How do you push back? What's the pressure that you can apply to push back from the boundary of unacceptable risk? And also, how do you know that you get closer? How do you get feedback that you get closer? Also connected to the idea of risk as a control problem in a goal-constrained environment is the question of whether you want to do minor changes of the code very often or major changes more rarely. How do you want to play that? How do you want to experiment to optimize locally? How do you want to do that? This idea, this model also embraces the idea that risk measures can be risky. Risk measures can be risky. That's what it is to work in a goal-conflicted environment. And we can see one example from your world. I showed you this topic before, Twitter outage caused by human error. And it also says domain briefly yanked. And this was the t.co domain that you guys at Twitter use for link shortening. And the chief research officer at F-Secure afterwards tweeted that this event illustrates how short links make the web more fragile and harder to archive. So was this only for me to be able to write longer URLs in short tweets? Well, look at what Twitter says about why introducing this t.co domain, which later was constructed as a fragile T in the system, a risk in the system. Look at the third point of motivation here. Having a link shortener protects users from malicious sites that engage in spreading malware, phishing attacks, and other harmful activity. Essentially, it's a risk management measure. It's a safety measure, the t.co domain. A safety measure which later became a risk or a fragility in the system. So from this control problem theory of risk, we would say that risk and safety are products of the same kind of processes in goal-constrained environments like the one that you are working within. Risk and safety are products of the same kinds of processes. So not only is risk a product of variability, which was a threat in the idea of risk as a product of unreliable system components, but safety is also a product of variability. Risk and safety, products of the same kind of processes. So based on these ideas, based on the idea of risk as managing complexity, where we use ideas of the path dependency of risk and risk as a control problem, where do we go to manage risk? What do the great thinkers here say? And they have some ideas. What they typically say is that organizations that are really good at this tend to keep the discussion about risk alive even when everything looks safe. And they do so by constantly inviting minority opinion, inviting doubt, inviting, I don't feel good about this, and taking that seriously. They do so by constantly debating the location of the boundaries and the distance to them, boundary of acceptable risk, for instance. And remember, we said that in a complex system, each actor will essentially experience different systems. So the debate here is a highly fruitful risk management exercise. Organizations that are typically good at this also constantly monitor the gap between work as prescribed and work as performed, realizing that there will always be such a gap, but also questioning whether the gap shows tendencies of normalizations of risk, for instance. And given that risk and safety are products of the same kind of processes, organizations that are good at this, they focus on understanding how people make the trade-offs that guarantees safety, and not seeing people as an inherent risk in the system, but as a guarantee of safety in the system. This is what Eric Holnagel really emphasizes, one of the great thinkers in this field, really emphasizes when he says, safety management, it's not about avoiding negatives such as incidents, accidents, and errors. Safety management is indeed about achieving. It is about the constant trade-offs that you make. So which one is it? Should we see risk as a product of your inherent unreliability, or should we see risk as a product of the complexity itself of the systems that you work in? Well, as the annoying little academic that I am, I will of course argue that we asked the wrong question from the beginning. And I will use Paul Slovic to help me out in making that argument, saying that what we should see risk as is as a game. We should see risk as a game played between actors representing different values and different frames of reference. So how do you want to play that game? These two extreme views that we've drawn out now during this keynote would represent different frames of reference that you could compete for, so to speak, in the risk game. But also frames of reference that have their implicit values baked into them. Any account of risk, according to Paul Slovic, has inherent values, implicit or explicit. Whether we construct Google going down as the end of the world, we express certain values. Whether we express Google Glass as a great security threat or a fantastic opportunity and possibility, we express certain values. Whether we see, as the UN does, internet access as a basic human right, we express certain values. Whether we construct Snowden as a hero or a traitor, we do the same. We express values. So my final appeal to you this morning will be, make your values explicit. What are the values? In any of your accounts of risk, what are the values baked in to these accounts? What are the values guiding your perception of risk in web performance and web operations? Make them explicit, and you will have a constructive risk game played amongst you, I am sure. That will be my final appeal to you today. I will thank you very much for having listened this morning. These slides are already available at jbsafety.se. You can click your way back and forth through them, and when you come to a point where you say, this dude is not making any sense whatsoever, you continue the discussion with me on Twitter or by writing me an email. Thank you so much for having listened. Really appreciate to be here today. Thank you.